So, hi guys. So, I'm Dr. Goh here. Okay. So, today I would like to explain about chapter 3, which is about the actions and load distribution. And this slide is prepared by IR Dr. Muhammad Sofi bin Muhammad Noor. Okay. So, what is actions or loads? So, action and loads are primary considerations in any building design. It can be defined as an internal forces that a building must resist to provide reasonable performance, either safety or either serviceability, okay, throughout the structural design's working life. Okay, so you design to have a working life of 50 years, so it must be able to last until 50 years or above. Then the anticipated loads are influenced by a building intended use, which is occupancy and functions, okay, configuration, which is size and shapes, and also the location, which is about the climates and site conditions, such as if it's located at the earthquake zone, at the four-season country with winter and the snow loads. Okay, so ultimately the type and magnitudes of the design load affect the critical decisions such as material selections, construction details, and architecture configurations. Thus, to optimize the value, okay, the performance versus economy of the finished product, it is essential to estimate the design load realistically. Okay, so now we look at the loading estimations. So for loading estimation, it is very important. You must estimate the enough loadings. Okay, so we have few elements here. You can see that the first is slab, and then we have beam, and then we have columns. After that we have foundations. So normally we start with the slab, which is okay. So most of the load we have permanent load, which is the dead load, and also the variable action, which is the live load. Okay, permanent load action means the load is permanent on it, and then the variable action is which is like varies, and then it's like movable. Okay, so for permanent load for slab, we have self weight, means the weight of itself, finishes and services on top of it, and also the ceiling if let's say it's on the first floor and above. And then the unit is in kilonewton per meter square. So every 1 meter square, how much is the load times the area of the load slab, then you can get the total loading. And for beam, also we have permanent actions, which is including the distribution from the slab, which the load will distribute from the slab and the roof to the beam, and then beam later to the column, and column finally to the foundations. And also to estimate the permanent action, we have cell weight for beam, and also brick wall. Let's say you have brick wall on top of it, so all of this must include in the permanent actions. And for variable actions, we have distribution from the slab, which is the live load from the slab, and then it will distribute. Okay, and then the unit is in kilonewton per meter. And next is column. So column, for the permanent actions, we have the distribution from the beam, okay, and cell width of the columns. So only these two. And also variable action, we have distribution from the beams. Okay, and then the unit is in kilonewtons, okay, which is in point load. And foundations. Foundation, the permanent load is distribution from columns and cell width of footing. Okay. So variable actions is distribution from the columns. Okay, it's in kilonewton. So you can see that the loading from the slab will go to the beam, beam will go to the column, and go to the foundations. So for loading estimations, okay, the permanent actions on slab. So we go to the slab first. So you can see that the self weight of slab, how are you going to calculate it? So first is the slab thickness times the unit weight of RC. RC here means the concrete weight, okay, the reinforced concrete unit weight, 25 kilonewton per meter cube. Okay, that said, this is for the concrete grade 25. So you will calculate the hash times the unit weight, then you get the unit is in kilonewton per meter square. So in common practice, minimum slab thickness is 100 millimeter, and the maximum slab span should be not more than 36 hash. Okay, and for finishes, what is finishes? Okay, so finishes is depending on the floor finishes assigned by the architects. Refer to the manufacturer catalogs. So for example, if you use this White House ceramics, 600 millimeter times 600 millimeters, okay, so 1.44 meter square, and then the weight is 31.68 kg for the tiles. So the ceramic tiles is 31.68 kg from here times 9.81 over 100. This is convert the kilonewton and the kg to kilonewton over 1.44 meters square. So you can convert it to every 1 meter square because this load is for this load is for this meter square. So after you calculate this, you will get 0.22 kilonewton per meter square for the ceramic tiles. And how's about the ceramic randle? Okay, the ceramic randle here is using 30 millimeter thickness, so is 1900 kg per meter cube, which is about the ceramic randle is like the mortar. Okay, so this is 1900 kilonewton per meter cube, which is the density, times the convert to the kilonewtons, and then times the thickness, so you will get 0.56 kilonewton per meter square. So you need to total up these two, okay, which is the total finishing load equal to 0.22 plus 0.56, so it's equal to 0.78 kilonewton per meter cube, meter square, sorry. So the ceiling weight is normally a range from the 0.3 to 0.5 kilonewton per meter cube depending on the ceiling types. Okay, so also the variable actions of slab, where you can refer to the Eurocode ones. So in Eurocode 1 you have many categories, so you need to read it in the Eurocode for each sections. Okay, so from category A1, A2, A3, A5 up to class 5. Okay, so this table is combine all these category and then give you a summary about what is the QK. Okay, this small letter, okay, is in kilonewton per meter square. Okay, and this capital QK is in kilonewton. Okay, choose the one that needed. So characteristic variable actions QK, okay, act on the slab is caused by people, furniture, equipment, and anything. So which is the variation in magnitudes, time depend is considered. So let we go through the example used. So you can see that for all usage within the self-contained dwelling system, okay, the QK is 1.5 for QK and this one, and then for 2.0 for this capital QK. Okay, and then we also have the bedrooms and dormitories, and then bedroom is hotel, motels, hospital wards, toilets, and then A5 is balcony in single family dwelling units, and A7 is balcony in hotels and motels. You can see that a little bit difference at here. And B1 is office for general usage. C5 is assembly area without fixing seating, concert halls, bars, places of worship. Okay, for the area like we need to have a big areas like for churches and the malls. Okay, and D1 over D2 is the shopping areas. E is the general storage, or either E17 is the dense mobile stacking in warehouse. And F is the gross vehicle weight. So you can read the Eurocode 1, you can read through the EC1, and then you can have the value of QK for this both. Okay, so also in the MSEM 1991, okay, -1 2020, which is the table National Annex 2, okay, from the Malaysian National Annex to Eurocode 1. Okay, you can refer this in your Eurocode. Okay, categories for residential, socials, commercials, and administration area, including additional subcategory for Malaysia. So you will have to design the building according to the specific use. So how you going to decide the variable action on slab? So you need to categorize first. So first you have A, which is the area for domestic and residential activities, and B for office area. So C for area where people may congregate, the exceptions of area defined under category A, B, and D. Other than that, you will have category C here, area where it's same thing, and then but then the subcategory is different. Okay, you can read through all these examples. There are lots you can read through in the table. And A2, and also D is the shopping areas. So when you design a shopping center, And then the shopping areas, you need to use this. And we will design for domestic area, then you need to go to category A. So you can go through the table of this and read through one by one what is the subcategory. Okay, so we go to the loading estimation for beams. So how you estimate the self-weight of beam? Okay, if it's a rectangular beam, then just easy. You just take the B times the H times the units weight of concrete. But if it's a flange beam, okay, so means that this is the slab on top, and then you have a flange beam that compound of it. So the self-weight is equal to BW times H minus HF, which is the area of here, which is H, the area of the H here. Here is equal to H minus HW. Okay, so the self-weight is B times H minus HF times unit weight of concrete. Then you can get the area of this. Okay, area of this. Because what? For this area is already considered when you calculate the slab. So, how's about the self-weight of columns? Self-weight for columns, okay, is B times H times L times unit weight of concrete. So this is the B, this is a H, and this is the L, times the unit weight of concrete. And then so for self-weight of foundations is BF times LF times TF times unit weight of concrete. So basically is the volumes times the weight of concrete, then you will get the self-weight. So for brick wall, okay, brick wall you can use 2.6 kilonewton per meter square times wall height. So how tall is your building? You just time this 2.6 kilonewton per meter square. Okay, so you can get per meter run. So loading distributions. So how is the load distributed? So as I explained it briefly before. Okay, so distribution actions, you can see that this is the slab. Okay, the load is from the slab, and then it will either going to the beam. So here you have a beam here, you have surrounding, you have beam here. So from the slab it will go to the beam, and from the beam it will go to the, here also have a beam, so it will go to the columns. So from the column it will go through the foundations. Okay, so basically there are 4 steps. So from the slab to the beam, beam to the column, and column to the foundations. Okay, and foundations to the solid rock area. Okay, so actions that are applied on a beam may consist of beam self-weight, permanent and variable actions from slab, actions from secondary beam, and other structural or non-structural members supported by the beam. So do you know what is primary or secondary beams? Secondary beams don't have the column support. So secondary beam will not distribute the load directly to the column. So it will distribute the load to the primary beam which is connected to it as a point load. Okay, so the distribution of slab actions on beam depends on the slab dimensions, supporting by the system and boundary conditions. And it is important to determine the type of slab using the following criteria. So basically slab we have 2 types, which is the one-way slab and another one is two-way slab. So what is the difference? Okay, so here we have Ly and also Lx. So when we look at a plan, okay, architecture plan, so how are we going to decide which is Ly and which is Lx? So Ly is the longer edge, and then the Lx is the shorter edge. Okay, so Ly over Lx is the value is greater than 2.0. Okay, it is one-way slab, means it will only distribute to either Ly or Lx. So if it's greater than 2.0, it will distribute to the Ly. You can see that. Okay, so it will distribute to here and also here. It will not distribute to Lx. Okay, it will not distribute to here. And then, okay, so for two-way slab, you can see that here, okay, Ly over Lx is less than 2.0 or equal. So means that the load will distribute to all edges. Okay, to here, to here, to here, and to here. And how are you going to calculate it? There are the methods for it. Okay. So one-way spanning slab supported by the beams. Okay. So we can see that the W's is equal to 1/2 times N, which is the load. Okay. You calculate. Okay. And then times the Lx, the length of the span. And then the unit is kilonewton per meter. Okay. And then this is only for the beam of Ly. So as I explained before, if it's the one-way slab, so the load will distribute to the longest edges here and here, AC and BD. Okay, half. Here 0.2 means you distribute half to the left and half to the right, and Ly and Lx will get none. Okay, and two-way slab panels freely supported along 4 edges. Okay, you can use this formula, which is W equal to N Lx over 6, and then in the blanket 3 minus Ly over Lx power of 2. Okay, and then for the AB and CD, which is the shorter edges, you need to use W equal to N Lx over 3. Okay, so this is the way to calculate. But there are also alternative method which is considered various support condition and slab continuity. The methods are: number 1, slab shear coefficient table from 3.15 PS8110. Okay, number 2, yield line analysis, and number 3, table 63, reinforced concrete design handbook by Renault. So for the first method from the BS8110, okay, table 3.15, you can refer to the BS8110. You can see this table. So we have 9 cases. So we have 9 cases of this. We will go through one by one. Okay, so this is case. Let we go to the first, the case 1. Okay, so the case 1 here, 4 edges continuously. Okay, means 4 edges continuous. Means this is the case 1. So you can see that this 1, 2, 3, 4. These all 4 cases, the 4 edges are continuous. Okay, so you have the value of BVX and also the value VVX for the value of Ly over Lx. So you calculate the Ly over Lx, and then if it is 1, then you refer to this row, and then if 1.2, and then it's this, and then up to 2.0. If greater than 2.0, then is one-way span. So this is only up to 2.0 because two-way slab is less than 2.0 for Ly over Lx. And then the VBY is this value. So this is VBX and this is VBY. So you can do this. Okay. So case 2, one short edge discontinues. Okay. So one short edge discontinue means that here, case number 2, the longer edge is continue. This short edge is continue. This long edge is continue, but this short edge is not continue with other slab. Okay. So for the continuous edges or continuous edges, you can refer to this row, and then the short discontinuous edges you can refer to this one, which is no value. Okay. So for case 3 is one long edge discontinue. So we go to case 3. Case 3 is here. You can see that this is the long edge, which is no continuous. It's not continuous. Okay, it's not continuous. And then case 4, 2 adjacent edges discontinuous. So number 4 here, you can see that these 2 adjacent, one long and one short, is discontinuous. So you can refer when the continuous edge is what, and then the discontinuous edge, when the what is the value for continuous edge and what is the value for incontinuous. And case 5 is 2 short edges discontinue. So case 5 here, okay, you can see that from this one means no slab. So for case 5, 2 short edge here and here is discontinuous, but then the long edge is continue. And case 6 is 2 long edges discontinue. Okay, case 6 is 2 long here is discontinue, but 2 short edges are continuous. And then case 7 is 3 edges discontinuous. Here discontinue, here discontinue, and here discontinue. Only one long edge is continue. Okay, and then case 8, 3 edges discontinue and one short edges discontinue. So case 8 here you can see that this is discontinue, this is discontinue, and here is discontinue. Only one short edge is continuous. Okay, you can see that this is case 8, and case 9 is 4 edges discontinuous. So you can see that this case at 9 is not continue with other beam, other slab. So this is the loading distribution, okay, table to refer to get the beta Vx and beta Vy. So this is the example 3.1. Okay, so for loading distributions. Okay, so the question is, determine the characteristic permanent and variable actions on the beam FB1, which is here. Okay, so which is this beam, okay, which is 250 times 700 as shown in the figure above, and a brick wall of 4 meter height. Okay, so this brick wall is 4 meter height. It's sitting on the beam, and then the unit weight of concrete is 25 kilonewton per meter cube. Finishes is 1.0 kilonewton per meter cube, and brick wall is 2.6 kilonewton per meter square. Or this one is meter square, sorry. And variable action is 4.0 kilonewton per meter square. So let we see FB1. Okay, so FB1 here. So okay, so this is 8 meter. FB1 here and FB1 here. Okay, so this is 8 meter. And then from the precast slab, so the load will distribute to the FB1 here and FB1 here. Okay, so this is the FB1 here, which is 250 times 700. Okay, so the GK here for the beam. Okay, so as explained in the slide before, GK is the permanent load, permanent action, which is including the self weight of the beam, the brick wall, and the load from slab. And the QK is from the slab. Okay, so permanent actions, to calculate the GK for beam, we will calculate per meter. Okay, so the self weight is 0.25, which is the B, okay, time hash, which is the 0.7 millimeter, 0.7. Okay, this one is already converted into meter. Okay, times 25 kilonewton per meter 3, which is the unit weight. So after you time 0.25 times 0.7 times 25, you will get 4.375 kilonewton per meter. Means every 1 meter, the self weight of the beam will be 4.375 kilonewton. And the brick wall will be 2.6 kilonewton per meter square times 4 meter height, because the height of the brick wall is 4 meter. So you will get 10.4 kilonewton per meter. And for the slab, the thickness is 0.15, which is 0.15. We already convert to meter. Okay, times 25 kilonewton per meter power of 3. Okay, so this is meter just now. Okay, and then plus 1.0, which is the finishes. This is all provided by this is information is provided in the questions. Okay, so you solve this, you calculate, you will get 4.75 kilonewton per meter square. Okay, so this is the self weight of slab, self weight of wall, and self weight of the beam. So you total up, the total GK is 29.025 kilonewton per meter, which is every 1 meter you will have 29.025 kilonewton. Okay, so for QK, which is a variable actions, is from the slab. So just now variable actions in the question here is 4.0 kilonewton per meter square. So okay, we need to calculate the QK. So we know that QK here is W equal to 1 over 2 N times Ly. Okay, so the variable action is 4 kilonewtons, which is the N, and then the Ly is the 6, and then 1 over 2. So half times 4 times 6, you will get 12 kilonewton per meter. So after you draw the reactions here, you can get GK is 29.025 and QK is 12. So this is the permanent actions and this is the variables actions. Okay, so let me explain about example 3.2. Okay, so this is the plan. Okay, so let's go to the question. You can see that determine the characteristic permanent and variable actions, okay, the GK and the QK on beam 1, 3. Okay, so this is beam B13. You want to determine the characteristic permanent and variable action on this beam from B1 to 3. So given the following data, okay, unit weight of concrete is 25 kilonewton per meter cube. Finishes, ceiling and services is 2.0 kilonewton per meter square. And variable actions QK for all slab is 3.0 kilonewton per meter square. So first we need to calculate the action on slab. Okay, so first we need to calculate the self weight of slab, which you can look at the slab. Okay, so here we have 3 slab. We have FS1, FS2 and FS3. So all the thickness is 150 millimeter. So the thickness of slab here is 150 mm, which is equal to 0.15 millimeter times 25 kilonewton per meter cube. So you times the thickness, you will get 3.75 kilonewton per every meter square. Okay, and then the finishes given here in the question is 2.0 here, 2.0 kilonewton per meter square. So the total GK, which is the permanent actions, is self weight plus the finishes, ceiling and service. So it's 3.75 kilonewton per meter square plus 2.0 kilonewton per meter square. So it is 5.75 kilonewton for every meter square. And the live load here at the variable action, the live load here QK, variable action is 3.0 kilonewton per meter square. So we need to calculate the distribution of actions. So because here you can see that we have 3 slabs, okay? So we need to have LX and LY. So the longer span is the longer edge is the LY and then the shorter is the LX. So for the FS1, the LY is this, the LI is this. Okay, so for FS2, here is the LX because it's shorter, is 3000, and LY is here, okay, is 4000. So for the FS3 is LY is here because it's 4500 and here is 400 and 4000. So we need to determine either it is one-way slab or two-way slab. So for FS1, the LY over LX is 7.5 meter over 2.5 meter, so you get 3, which is greater than 2, means it's one-way slab. One-way slab here mean, okay, the load will distribute to here, okay, to here and here. You will not distribute to the shorter edge here, okay. And then the LY2 is 4 over 3, which is 1.33, is less than 2, and FS3 is 4.5 over 4, which is 1.125, also is less than 2, so it's also two-way slab. Okay, so the distribution is like this. So to the LY will be the trapezoidal load and the LX will be the trapezium load. Okay, so here also the same. Here LY will get the loading like this, and then the LX will get loading like this. Okay, so once you draw it, will become like this. So W1 is equal to 0.5 N times LX, and W2 is beta Vy times N times LX. And the W3 here is VBX times N times LX. So we need to determine the value of VBY and VBX using the British Standard Table 3.5. Okay, so we go to calculate the action from the slab. So for the FS1 is 0.5 N times LX. So it's easy. We get 0.5 times the N. Okay, for GK we get the GK from the first calculation, which is here 5.75. Okay, and then we times the LX is 2.5, so you will get the W1 GK1 7.19 kilonewton per meter, and W1 GK1 QK1 here is 0.5 times 3, which is the value for QK, the QK here. So you times, you get 3.75. Okay, so and then for FS2, now we need to get the beta B Vy. So how can we get it? Okay, we need to use the table 3.5. Okay, so the table 3.5 here. So just now when we calculate the value of the FX2, we get 1.33. Okay, so 1.33. Here we refer to this, and then the slab is like this. So two edges discontinuous. So we need to refer to this. So when you refer to this, you can see that VVY is 0.4. Okay, so the answer will be 0.4. Okay, you extract 0.4 times 5.75 times 3, you get 6.9. Okay, and then the QK is 0.4 times 3 times 3.0, then you get 3.6 kilonewton. So this is for FS2. Okay, so let's go for FS3. So to calculate FS3, W3 now is using VVX times N times LX. So remember just now the difference here is the VVY, okay? Because this is formula for beam at X, LX. And then this VVX is formula for beam at LY. So this one you need to be extra careful. If you use the wrong one, means you will get the incorrect answer. So how can we get this? Also the same, we need to refer to table 3.5. And then for FS3, LY over LX is 4.5 over 4, which is 1.125. Okay, so 1.125 here, you can see that for this table. Okay, so for this table, 1.125 is in between here. So 0.44 or 0.47, because this is for VVX. Just now we refer to VVY for the FS2, but for FS3 we need to refer to this value. So what we have to do now is, if you want to get a more correct answer, you need to use the cross multiply. So for cross multiply, you can see that I already show you here. So you need to do this is 1.2 minus 1.1 over 0.47 minus 0.44 is equal to 1.2 minus 1.125 over 0.47 times minus x. So you solve this according to this method, you will get x equal to 0.45. Okay, this is from your math foundation, so you can go back to practice this how to do it. So once you get x equal to 0.45, so let's recalculate this. So W3 GK3, okay, so 0.45 times 5.75, okay, which is the value from the calculation before, times 4, you will get 10.35. So the W3 GK3 is 0.45 times 3 times 4, so you will get 5.4. So this all value, once you get it, then you can calculate the action on beam. So action on beam, you need to calculate is beam self weight. So from the questions, okay, from the questions you already have the beam size. You already have the beam size, which is the 200 times 500, 200 times 500, all is the same, 200 times 500. So is 200 0.2 millimeter and 0.2 meter times thickness 0.5 minus 0.15. Why? Because we need to minus the slab thickness and then times the unit weight of concrete. So you will get the beam self weight is 1.75 kilonewton per every meter run. So here is every meter. So just now the slab is every meter square. So the span 1, 2, okay, for the span, so here you have span 1, 2 and span 2, 3. So for span 1, 2, the permanent action will be the FS1. Okay, so for here you will have FS1, FS2 and also the self weight. Okay, and here you will have FS1 plus FS3 and also the self weight if for this one. So for span 1, 2 you have 7.19, 6.9 and 1.75. So you total up this, you will get the value of GK. And for QK, so you will get the value from 3.75 and 3.6. All these are calculated from just now. Okay, you can see that 3.6 and 3.75. This is from the slab. So for span 2, 3, okay, FS1 is 7.19, FS3 is 10.35, and British and the beam self weight is 1.75. So you total up, you get 19.29. So for variable actions, QK is FS1 plus FS3, means it's slab variable actions. So it's 3.75 plus 5.5. Okay, 3.75 from FS1 and 5.4 from FS3. So you total, you get this value. Okay, so basically we already get the span 1 and 2 actions. So you can see that. So when we draw the free body diagram here, okay, so you input the value for the GK is 15.85, and then for the QK is 7.35 here, and the GK for the span 2-3 is 19.29, and the QK is 9.15. So this is the method on how you calculate the loading from this. Okay, so this example is until here. So thank you for watching.